Hey, welcome back to chemistry, and we are continuing on with chapter 4. And so I want to go over a class of reactions called ionic reactions, and they are in section 4.4 of your book. Your book calls them precipitation reactions, and so what they say for precipitation reactions pretty much applies for what I'm going to be talking about, which is ionic reactions. So they're, for the most part, they are the same generally. Now, one thing I want to do is kind of sort of set you up for understanding how ionic reactions in solution occur. So the ones we're going to be looking at are where we have water, and water is going to receive two compounds. And in this example, one compound is KCl, which is potassium chloride, and the other compound that the water will receive is silver nitrate, which is AgNO3. Now imagine when these compounds are dissolved into the water, what happens? Well, now we have an aqueous solution of ions, and the reason is both KCl and AgNO3 are very soluble salts, and so KCl will dissociate to potassium and chloride ions, and AgNO3 will dissociate into silver and nitrate ions. And so you have basically 4 different ion types in solution. So to understand an ionic reaction, it kind of helps to sort of understand that this basically happens. So you see that red K there? What will happen is the K will break off the Cl and it'll stick to the NO3 and it'll push off the Ag, the silver, and then the Ag replaces the K on the Cl. So you get those two product compounds. Now the K is stuck onto the NO3 and the Ag is stuck onto the Cl. And so I kind of call this a double switcheroo. It's also called a double displacement reaction, or it can be called a metathesis reaction. Importantly, when you have this reaction occur, the double switcheroo, there's something I want you to notice. So notice how in the reactant side of the equation, the potassium chloride and the silver nitrate, it says aqueous there. What that implies is that for both compounds, they're all ions dissolved in solution because those salts totally dissociated into ions in solution. But if you look at the product side, it looks a little bit different. What you can see is that there is KNO3, potassium nitrate, in aqueous solution. And so you can probably bet that that has completely dissociated in the water, producing potassium nitrate ions in the water. But look with AgCl, which is silver chloride. That's not aqueous, that's an S. So what has happened is as soon as you had silver ions exposed to chloride ions, they bound together to form a precipitate. And when they form the precipitate in solution, that is indicated by an S. That indicates that there is a solid there. So if it's forming a precipitate in solution, you can probably bet that that precipitate of silver chloride is considered an insoluble salt, and it is. And so keep in mind that with a lot of these ionic reactions, most of the time, but not all the time, most of the time, one of the products formed will be insoluble, and you'll have to use the solubility rules to sort of recognize which one it is. In this case, it's silver chloride. Now, how about the potassium and nitrate that formed? Well, keep in mind that really those ions are just kind of sitting there kind of watching what's going on. They're not sticking to each other really. So there you have potassium ions in solution, nitrate ions in solution. So they're watching the silver chloride stick to one another to form the insoluble salt. And so if they're watching what's going on, they are said to be spectator ions. And so you need to recognize that the soluble product ions, which are potassium nitrate, are the spectator ions. Okay, so just a note here, ionic reactions involve one or more reactants that are ionic compounds in solution. And I'm going to give you some examples on the PowerPoint, and then I'm going to write some out onto the glass board. So what we're going to do in these examples I have on PowerPoint is we're going to have to look at a sentence and write out a word equation that describes the reaction, then write out a molecular equation and balance it, then write something called a complete ionic equation, and then write out the net ionic equation for any precipitate that forms and identify the spectator ions. So here we go. So what we're going to do is we have an example here that I've written up. It says potassium chloride and silver nitrate are mixed together in solution, so it's an aqueous solution, and they form the product compounds, potassium nitrate and silver chloride. And so we have a word equation that describes this. So let's again sort of describe what has happened here so that you understand the relationship between the products and the reactants. So here in the beginning here, we have two compounds as reactants, potassium chloride and silver nitrate, and they're dissolved in the water. And basically what happens is the potassium breaks off and binds to the nitrate, while the silver breaks off and binds to the chloride. And so that gives us the products that I'm indicating here, which is the potassium nitrate and the silver chloride. So again, this is sort of a double switcheroo metastases or a double replacement reaction. So here I'm just writing out the formulas for each of these compounds. So I'm hoping at this point, if you were given the name of a compound, you could write a formula for it. For example, you may remember that Ag has a single positive charge and nitrate NO3 minus has a single negative charge. So you need one of each to form the compound. So it's just AgNO3. And so those formulas should be correct. Now the one thing we want to check is just to make sure that that is a balanced equation. In other words, for each element, do we have the same number of atoms on the product side as we do on the reactant side? And we do. Now the next thing we're going to have to do is write a general ionic equation. So this kind of helps us think about what is really going on in this beaker of water. What are we seeing? Are we seeing compounds or something else? And so this kind of points out that really the KCl is in the water, but it's completely dissociated when it hits the water into ions. So when you add KCl to the water as a reactant, it dissociates completely into ions because KCl is soluble, and so you get potassium chloride ions. And same thing with silver nitrate. You might remember that all nitrate salts are soluble, and so that should completely dissociate into ions. Now KNNO3, when you get the product form KNNO3, keep in mind that the K is not going to stick to NO3 for any length of time. It's going to be completely dissociated into ions, potassium nitrate ions. Now, silver chloride will not dissociate into ions, and the reason is because it is a precipitate, and we know it's a precipitate because it is an insoluble compound, so we indicate that with an S. Okay, now I'll bring up the general ionic equation. So what you're doing here is you're basically describing the true state of these compounds in each of the solutions. In the solution before you have the reaction and the solution you have after you have the reaction. So before you have the reaction, you really don't have KCl stuck together and AgNO3 stuck together. Instead, these are all just dissociated ions. So on the left side, I've written out what is truly going on in the water. You really have potassium and chloride ions and silver ions and nitrate ions. And then on the product side, you have potassium and nitrate ions in the water sitting there, but the silver and the chloride ions have found each other and they have stuck together to form the insoluble salt. And so here I'm just indicating there that that final equation with all those ions is called a complete ionic equation. So I'm just continuing on with this same example, and so I've rewritten the molecular equation up there. And what I want you to know is, let's take a careful look at the complete ionic equation. So what we're going to do is draw a net ionic equation that describes the formation of the precipitate. And so there are a number of ways you can do that, but I'm just going to show you one way. So one way to note is that which ions are on both sides of the equation. If they are on both sides of the equation, they can be canceled out to figure out what the net ionic equation is. And so we have potassium on the reactant side, we have potassium on the product side, so they can be canceled out when forming the net ionic equation. We have nitrate in the product side, reactant side, nitrate in the product side. And so those can be canceled out. And so we can't really cancel out anything more. We have silver ion and chloride ion, but what you can see here is that we don't really have those ions on the product side. Instead, we have the insoluble salt of silver chloride. So we cannot cancel the silver and chloride nor can we cancel out the AgCl, solid insoluble salt. So those are what remains, and so you write out what remains, which is chloride plus plus silver ion gives you the insoluble solid salt of silver chloride. And so that's called the net ionic equation. But when you write out a net ionic equation, usually it's going to be for an insoluble precipitated salt. And so all you have to do is identify which compound is the insoluble precipitated salt on the product side, which is silver chloride, and then indicate on the reactant side of the net ionic equation which ions are used to form it, which are chloride and silver ions. Okay, so let's do one that's a little bit more complicated. So here is a chemical equation I wrote out to describe a certain reaction. Basically, let me just kind of describe it to you. It's like you start out with a beaker of water and you threw in iron chloride into the water. And iron chloride is completely soluble and it will dissolve in the water. So you can imagine that's going to dissociate into ions. Sodium hydroxide is also thrown into the water. And so that is also soluble and it will dissociate into ions. And so what you'll get, again, is the sort of double switcheroo, where what will happen is iron here will leave chloride and bind to hydroxide, and sodium will bind to chloride. And so you get those product compounds formed. Now the NaCl that forms is soluble, so that'll be in the form of ions, but iron hydroxide is one of those compounds that is insoluble, and so we indicate that by writing a S there. Okay, so just to note that that chemical equation was not correctly balanced, so now I've sort of balanced the chemical equation. So the reason why I have to point this out is because this is going to be translated into your general ionic equation. So I want you to notice here, things get a little bit more complicated. So we have iron here in the general ionic equation. We get iron with the 3+ charge. We have chloride here. Now keep in mind that each chloride has a single negative charge, but there are 3 chloride ions bound to the iron. So we should see 3Cl minus. And same thing here, we have 3 sodium ions and 3 hydroxide ions. So you have to indicate that into the general ionic equation. And same thing with the product side of the reaction. If we have 3 NaCl's, 3 sodiums are going to be seen in the general ionic equation, and 3 Cl's will be seen in the general ionic equation. And also, we have that insoluble iron hydroxide salt, and so we don't write ions out for that. We just leave that as FeOH3. So just again to note that you have to sort of translate those coefficients into the general ionic equation if they are there in the chemical equation. And so here I'm just writing out the net ionic equation, and it also is describing the precipitation reaction for this reaction here. So what I'm going to do now is I'm going to write out on the board a bunch of reactions. And so first, for each reaction, what I'm going to do is write out a word equation for the complete reaction. Then I'll write out a molecular equation and balance it. And then I'll write out a complete ionic equation. And then I'll write out any net ionic equation for any precipitate that forms and then identify the spectator ions. So let's try the first one here. Okay, so we have an aqueous solution of calcium chloride is mixed with a solution of lead nitrate. So I'm just going to write it out as a word equation. So we have calcium chloride is mixed in water with lead nitrate. Okay, so one thing I want to do is kind of predict whether what kind of state symbols we should have in here. So these salts are dissolved in water. So the question is, are they soluble or are they insoluble? If they're soluble, then they get the AQ state symbol. If they're insoluble, then they get the S. And so we have calcium chloride, and I think you can look it up, and what you'll find is that is a soluble salt in water. And the same thing with lead nitrate. That is also a soluble salt in water. So if that is the case, we write AQ to indicate that these will truly be ions in water. Okay, so the next thing I need to do is predict what the products will be and what the state symbols will be for those products. So you might remember that what happens in these ionic reactions, if you have two ionic compounds, you should just assume that the calcium breaks off the chloride and binds to the nitrate, and the lead breaks off the nitrate and binds to the chloride. And so now we can sort of predict the products. And so now we get calcium nitrate. I'm going to write this down here. These are the products, calcium nitrate. And we also get lead chloride. So I'm going to write this here, lead chloride. Okay. So the next thing we need to do is write out state symbols for these compounds. So what you might remember for the product compound calcium nitrate, all nitrates are soluble, and so it should be just ions in solution. So I'm going to write AQ here. And so lead chloride, this is one of those halide salts where it has lead in it, and if it does, then it makes it insoluble. So this will be an S here. So we have calcium chloride plus lead nitrate gives you calcium nitrate plus lead chloride. Okay, so one thing I definitely want to do is just to make sure that this equation is balanced before I go any further. So here I have one calcium here on the left side of the equation, one calcium on the right. Calciums are balanced. Nitrates are on the left balanced with nitrates on the right. How about chlorines? Two on the left, two on the right, those are balanced, and the leads are balanced. So this appears to be a balanced equation. So now we need to write out the general ionic equation. So we have calcium 2 plus, and so here what I'm doing is write out an ion for each of these ions in the compound. And I need to indicate the state, which is kind of a pain. Now be careful here. I'm about to write a mistake. A lot of people tend to write Cl2. This is not correct because this implies that really coming off the calcium is you have two chlorine atoms bound together to form diatomic chlorine. That is not what is really going on. Instead, what is going on is in this salt you have two different chloride ions bound to the calcium. So when this hits the water, the calcium releases two chloride ions. So it should be 2Cl minus aqueous. So that should be correct. Okay, for lead you need Pb2 plus aqueous. And then nitrate, we have two nitrates released, 2NO3 minus aqueous. And then we need to write out the ions for the calcium nitrate because that is also a soluble salt. So it's going to be calcium 2 plus aqueous. And then we have two nitrates again. And then finally, what we want to do is we have lead chloride, which is insoluble, right? So we do not write this as ions because this is going to be an insoluble salt. So we want to write plus PbCl2 solid. So that should be correct. This is the general ionic equation. Okay, now we have to write a net ionic equation. So there are a lot of ways you can think about it, but the way I kind of think about it, which is pretty easy for me, is I think about what ions do I need to have stick together to form the insoluble salt, which is lead chloride here. So the net ion equation, which I'm about to write here, is I need one Pb2 plus in aqueous solution, and then I need two chloride ions, also in aqueous solution, and then this will form the lead chloride insoluble salt. And so this down here is the net ionic equation. Now, once we've done all this, let's think about what the spectator ions are. So one thing that is helpful to remember is that with spectator ions, they are never found in the reactant side. They are always found on the product side of the equation. And basically, the spectator ions are the ones that are watching the insoluble salt formed. So if you have lead chloride here, it's being formed, you can think of the calcium and the nitrates as the spectator ions. You're sort of watching that insoluble salt being formed. So the calcium and the nitrates should be the spectator ions. Okay, and just for completeness, let me include state symbols up here, because on your test they may ask for that. They might ask for state symbols in the general equation. Okay, let's do the next one. Okay, let's try the next one. So an aqueous solution of sodium acetate is mixed with ammonium chloride. Predict the products and answer A, B, C, D, and E above. Okay, so we have sodium acetate and it's mixed with, it looks like ammonium chloride. Okay. And so the first thing you need to do is kind of predict the products of the reaction. So that's not so difficult. And so you just imagine here in this first compound, sodium breaking off the acetate and then replacing ammonium and sticking onto the chloride. So sodium is over here and binds to the chloride. And then an ammonium ion breaks off the chloride, replaces sodium, and sticks to the acetate. So that allows us to predict what the products are. So the products are going to be, it looks like sodium chloride. So let me write that down here. Sodium chloride and ammonium acetate. Okay. Now, I'm going to add state symbols at this point. So you might recall that when you have an anion, that is an acetate, in a compound, all compounds with the acetate anion are soluble. So all of them are. So I'm going to write an aqueous here to indicate that this would totally dissociate into ions. With ammonium chloride, you might remember that all compounds with ammonium ion are soluble. So we're going to put this as aqueous. Sodium chloride, so you probably already know that sodium chloride is considered very soluble, but the reason is, according to the solubility rules, is that sodium is, when bound to anything, any kind of anion is going to be soluble. So we're going to write aqueous here. And then we have ammonium acetate. That's a little trickier. You're thinking, oh, this one's the precipitate, right? Wrong, okay? This is the point I'm trying to make, is that you may be thrown a curveball and that there's some ionic reactions that can occur that do not form precipitates. And so how do we know that? Well, all acetate compounds are soluble and all ammonium compounds are soluble. So this ammonium acetate is not an insoluble salt in the water. This is going to be soluble ions in the water. So we can continue with this problem, but just keep in mind that when you have products formed, we will get no insoluble precipitate formed in this reaction. Okay, so let's go to the next step. Let us write an equation, chemical equation for this reaction. So you might have to remember what the formula for acetate is. It is C2H3O2, bound to sodium. And so let me include the state symbol here. Ammonium chloride is NH4Cl, aqueous. And then sodium chloride is NaCl, aqueous. And then ammonium acetate is NH4C2H3O2 aqueous. So far so good. So now let's check to make sure that this equation I've written is balanced. So one sodium on the reactant side, one sodium on the product side, an acetate ion here on the reactant side, just one of them. One acetate ion on the product side, one ammonium on the reactant side, one ammonium on the product side, and the chlorines, one on each side. So it looks like a balanced equation. Now, can you go through the tedium of writing out a general ionic equation? So let me do that, okay. So the nice thing is these are all soluble salts that dissolve well in water, so you can write out all these compounds as ions in the general ionic equation. Again, we have no precipitate here. So let's go ahead and do this. For the general ionic equation, I'll try to do this as fast as I can. Sodium plus aqueous plus acetate. Do you remember what the charge is for acetate? The charge for acetate is a single minus. Aqueous plus ammonium. NH4 plus is the charge for that, aqueous, plus chloride is a single minus, aqueous. And then we have the arrow, and then we write out the products. So it's going to be Na plus, aqueous, plus chloride minus, aqueous, plus NH4 plus, aqueous, and then plus the acetate ion C2H3O2 minus aqueous. So this is a correct general ionic equation. So you might ask yourself, is there a net ionic equation? Well, there would be a net ionic equation if we had an insoluble salt form, and we don't have one in this problem. So there is no net ionic equation describing the precipitation because, again, there's no precipitation that's being formed. Now, how about the spectator ions? Well, they're not really watching a precipitator or precipitate form, but I think you can sort of assume that all these ions, because they're just kind of sitting there doing nothing, all these ions, the sodium, the chloride, the ammonium, and the acetate ions in the water as products, all four of them are spectator ions. Thank you for listening. We'll see you next time.